This video will focus on a few different concepts, but the overlying concept for this video is equilibrium. Okay? You need to be able to understand equilibrium graphically. You need to be able to write something called an equilibrium expression. You need to predict at equilibrium whether reactants are favored or products are favored, and you also need to be able to calculate concentrations of reactants and products at equilibrium. Okay, so those are our main goals we're working on, and we'll continue to flesh them out in class. But one thing I want you to focus on this unit is what these learning targets are actually asking, because that is how the test is written. So to get into equilibrium, you have to understand reversible reactions. Let me tell you that most of the reactions we've done in class are not reversible reactions. When you put the reactants in, they react together and become product, and that's it. That's the end of the story. What a reversible reaction is a reaction that could occur in both directions. Okay? And it does occur simultaneously in both directions. So as your reactants become products, your products are also reforming or rearranging to become your reactants again. So this example right there, that SO2 plus O2 becomes SO3. As SO2 and O2 hit and rearrange, they become SO3, but SO3 actually interacts with itself and redecomposes into SO2 and O2 simultaneously. And you'll see here for the first time we have a double arrow. Okay, we have an arrow that's pointing in both directions, meaning this reaction proceeds in both directions. Pictorially, if you look at this, when we have SO2 and O2, we haven't reached what's called equilibrium yet. Okay, your reactants are there and they're becoming product, and if your products are there, they're becoming reactants. It's when you have both reactants and products that this reaction could be considered at equilibrium, and we'll talk about what that means. An example reversible reaction that you guys all know is photosynthesis. Okay? You have glucose basically combusting into CO2 and H2O, which is oxidation, right, what we do in our body. And then the reverse direction, photosynthesis, where you take carbon dioxide and water and make glucose. You see what you have on the screen is what's called a reaction pathway. It's the amount of energy required to make this reaction possible. We have a certain amount of activation energy for our reactants both times, and then a certain amount of energy being released. What a reversible reaction really means is that it is possible and there's enough energy available to go back over this reaction pathway. Okay? If you start with glucose, there's enough energy available to get to the activation energy, which is the peak, and then your products are formed. But if you have it the other way, if you have those CO2 and H2O as your reactants, there's enough energy available to get back over the reaction hump and back to glucose. Now, thinking about it this way, you'd say, well, isn't every reaction reversible then? Because all you need is enough energy to get you back over the activation energy and back over the pathway in the reverse direction. It's not always possible to reverse. Okay? Maybe there's not enough energy available just in the environment. Maybe we could add enough energy to it to make it happen, but there's not enough energy available. The difference between just a reversible reaction and one that's actually reversing in reality, and if you look at this reaction, it's a good example, is that a reversible reaction, generally speaking, it will produce enough energy to get itself back over the activation energy hump to be able to do the reverse. So a lot of times a reversible reaction looks just like this one on the screen, in that you have some amount of energy input to get to your activated energy, but then the amount of energy produced is enough energy to go back up over the activation hump and back to the other direction. Equilibrium then is a point where nothing is changing anymore. If you think about a reversible reaction, reactants are becoming products, products are becoming reactants, back, forth, back, forth, back, forth. You're like, well, when does it stop? That's the truth, is it doesn't. Okay? What we find is we get to an equilibrium point. An equilibrium point is when the rate at which your reactants are becoming products is equal to the rate at which your products are becoming reactants. Meaning, as some of the product is made, the product goes back to reactant, and you can't notice a measurable change. lots of things are moving, lots of bonds are being formed and broken, but you can't actually measure it because the rate at which they're being broken and formed is equal in both directions. I'll show you what this looks like in lab with a demo, but the biggest thing to know is that when we're dealing with equilibrium reactions or reversible reactions, there's an equilibrium point, and the equilibrium point is when the rate of moving from reactants to products is equal to the rate of moving from products back to reactants. If you look at this graphically, right here I have two different graphs. Okay? One is a graph of the concentration of your different reactants and products over time, and one is a graph of the reactant rates over time. What you'll notice on the right is eventually we come to a plateau where your two lines intersect. Okay? That's because at equilibrium, at the point of no more change, no more measurable change, your rates are equal. The rate at which the forward reaction goes is equal to the rate at which the reverse reaction goes. But what I want to notice about the concentration graph is your lines do not bisect. Equilibrium does not mean I have the same amount of all of my stuff. It just means the rate at which one is produced is equal to the rate at which the other is produced. So your amounts of reactions and products do not end up being the same at equilibrium. What we know at equilibrium is that the rate is equal and that the concentration doesn't change. The concentration is consistent at the equilibrium point, but the concentrations are not equal. So how do we calculate equilibrium? It's important to be able to calculate equilibrium because otherwise, dealing with reversible reactions, you would never be able to predict how much of anything you have because you wouldn't know. You'd be like, well, I have some amount of product and some amount of reactant, but it's possible for me to measure that. Instead, we have something called an equilibrium constant. And it is a constant that is solely dependent on the reaction you're working with. And it's just a constant that has a relationship between the amount of product formed and the amount of reactant formed at equilibrium. That amount specifically here is concentration. Okay, it is usually molarity, so moles of solute per liters of total solution. And what it is just a ratio of the concentration of product divided by the concentration of reactant at equilibrium. Okay, that's your equilibrium constant. To create one of these, if given a chemical reaction like the one on the screen, where small a, small b, small c, and small d are your coefficients, and the large letters are your actual substances, then the products go on top, the reactants go on bottom, and it's the concentration of each component raised to its coefficient. Okay? So like the concentration of C to the C, and the concentration of D to the D, to the coefficient on each substance. So you can see for KEQ, it's just a ratio of the amount of product versus reactant. We take into account the coefficient, and the reason is because that tells you how these things are all related in terms of their recipe. So you have to take that into consideration. KEQ can actually tell you a lot about your equilibrium because the value of KEQ tells you which direction is favored. And what that means is at equilibrium, again, the rates are equaled, but during the course of the experiment, you potentially produced more product or more reactant depending on what the equilibrium constant is for your reversible reaction. If you find you have a KEQ that's greater than 1, that means the products are favored. And if you look at the math, it should make sense. To get a number that's over 1, your concentration of products has to be bigger than your concentration of reactants, meaning you have more product than reactant, meaning over the course of the equilibrium, you favored the production of product over the production of reactant. Again, eventually the rates were equal in terms of how much, but overall you formed more product. If your KEQ is less than 1, that means your reactant is favored, because to get a ratio that's less than 1, the denominator has to be really big. And the denominator is the concentration of reactant, so that means the reactants have a greater amount being produced, and that is favored. Pictorially, here's another way of looking at it. So if you have a small k, again a k that's less than 1, you notice that you have a lot more reactant than product being formed at equilibrium. Again, it's dynamic. The blue and the red balls will change as they continue to react, but the ratio will stay consistent at equilibrium. If you have a large K, like at the bottom of the screen, then you have a lot of product and not a lot of reactant. Okay. And then if you have a K kind of in the middle between having a small and a big, usually we say a K of about 1, then your ratios are equal and you have pretty equal amounts of both reactant and product. So how do you write an equilibrium expression? Well, we're going to write one for both of these equations that are on your screen. The most important thing is just to remember that it's always a concentration of products over the concentration of reactants, and then you raise it to the power of its coefficient. So for the first reaction, the product is NH3, and you're going to raise that to the coefficient of 2. And you would divide that by the concentration of N2, which doesn't have a coefficient, so you'd leave it. And then you'd multiply N2 by the concentration of H2, which needs to be raised by a power of 3 because of the coefficient. The next one, your product, is SO3, which has a coefficient of 2 on it. And then you have 2 reactants, SO2, coefficient of 2, and then O2 with no coefficients. So this is what's called an equilibrium expression. Okay, it's an expression of how we can calculate KEQ for a reversible reaction. If I knew the concentration of product and the concentration of reactants at equilibrium, I could calculate what the equilibrium expression is. Or if I knew the equilibrium expression, I should be able to predict concentrations of reactants and products at equilibrium. That's it for tonight. Go ahead and do the form and have a nice night.